Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have The Last Ninja, published in 1987 by System 3, developed by Mark Cale and John Twiddy. So for those unfamiliar with this game, let's have a quick little run through the intro sequence, and then we'll have a quick run through some technical details about the game that we can see within the ICU debugger. This intro is actually a nice little intro. It's got a really lovely little dissolve effect between two different bitmaps. The piece of music is of course awesome. There are two bitmaps in two different banks, and the main bank with the actual animation and the dissolve going on is in the first bank, bank 0. There don't seem to be any extra characters. The text screen in the top right hand corner shows that there is some data hanging around from the load. You can see up in the top left it says please wait 2112 and all sorts of stuff like that. That's actually part of the auto run loader, which we'll have a look in much more detail later on. So the load for this is actually quite quick, relatively speaking, and you go straight into the game. Now this of course is the disc version. There wasn't any tape turbo load or anything like that. So we want to find where the bitmap is first of all, and the bitmap for the game data is obviously in the last VIC bank, up at C000 onwards. Now, when the player character wanders around, it's actually updating a very few number of sprites up at the start, towards the start of the last VIC bank. And it seems to copy these sprites. Well, it updates a sprite into a single place in extended 0 page. Well, maybe not extended 0 page, but anyways, it's up right at the top of memory, up right near the very beginning, and it seems to then copy that work in progress sprite up into memory. Perhaps it's doing some mirroring, perhaps it's doing some compositing or something like that. But what is important is that it seems to be copying sprite data from this area in memory. There's a lot of sprite frames, actually. Moving backwards and forwards, we can see that it is just using these two different banks of sprites here. It's basically double buffering the sprites, whereas we have a single on-screen bitmap for the game. You can see how it redraws the game bitmap. It renders from back to front and basically pastes in a whole bunch of brushes using the bitmap screen data. I'm actually attempting to run through the level very quickly here because I wanted to show how the sprite masking was working. This isn't a very good spot. I'm going to try and find a different spot where we can see how the sprite masking works. I'm not doing too well. Leave me alone. There we go. Let's see. Can I jump over here? Yes, I can run away. Run away, run away, run away. Still running away. Okay, so here we are. This is the point in the level that I wanted to get to. Now, the Commodore 64 does have the ability to move sprites in front of and behind certain screen elements. However, it's not going to work very well because it doesn't work very well in multicolored mode. It only appears with sprite priority in front and behind certain colours, whereas in this bitmap screen we want to actually properly mask out the sprites, have the characters appear in front of the sprites. So if we have a look at the sprite data, you can see when the sprite frames are being... Let's go back. You can see when the sprite is wandering behind something, the actual sprite data that's copied across into the double buffered sprite blocks here, sprite slots, we can see that it copies in the sprite frame and then it masks out what should be hiding the actual sprite. So there's a two-pass, if you like. It decompresses the sprite frame into place and then it masks out the sprite data that should be behind the characters. Now, this was a really clever trick. It's quite CPU intensive, but you know, the game has a static bitmap screen, so there isn't much to worry about in terms of too much time being used. There isn't any scrolling or anything like that going on, so the game can concentrate on double buffering just the sprite animation frames. And when I was young, when this game came out, I thought the quality of the graphics was fantastic, and actually each iteration of the game improved upon the graphics that we're seeing. So, of course, as is usual for this part in the game, I'm not doing too well trying to jump over the river. I always used to die here as well. Gosh, the controls were quite finicky. Oh look, I managed to get across. Amazing. Here's something. What is it? Is it a sword? Oh yes, it's the sword. And there's the game over screen with the press fire to start a new game. So let's have a look at the first file on the disk. We're going to load it without "1" on the end, so we're going to load it into our basic area of memory. We can see probably a sys with 2112 and a press, or type something and press whatever, or please type and then press. So let's have a look at what we can see when we do a list. It's loaded about 6 banks, 6256 byte chunks, pages, sorry, of memory that we can see from 0800 up until D00 roughly. And then if we do a list, we can see that it's printing a sys2 and 12, and we can see that if we do a disassembly of 2112, it seems to be, well, not doing very much. It seems to be just reloading, or doing a request to reload the file, but with basically a "1" at the end, which tells it to load the file where it's telling it to load, instead of us telling it where to load. Right, it's just turning off kernel messages, and it's just, which doesn't do very much. It just, I think this is turning off loading status update messages and stuff like that. And then just double checking here, FFD5. This one should be obvious to anyone who does any kind of like work in the kernel. It's load RAM from device. Yep. So there we go. Very short amount of code. So why is it loading so much? Well, it looks like it's loading a whole bunch of data. Doesn't look very codish. Some of it does, but not very. Anyway, so let's see what happens if we do load that file where it says it wants to load. Here I am in ICU trying to find gosh, I'm trying to find the star again. I can never remember where it is. And then of course when I'm not thinking about it, I type it straight away. There it is. Okay, good. Now I've loaded it back into basic again. And when you run it, sorry, there we go. It does a load, it loads the intro. Let's do a hard reset and then do a proper load, how it's meant to, and we can see it loads a whole bunch of stuff up into memory. The memory pattern indicates it's just filled the whole of memory. We can see the whole of memory has been filled with a repeating pattern. So it's definitely auto-running code, but it is auto-running code way down low in 0 page. Then it runs the intro. So let's have a little look more about this file. See if we can figure out how it auto-runs. So I'm going to use the C1541 tool to extract the files. We've got 4 files, all of the same length. Let's just make sure the files are identical. Pretty sure they will be. Same. Also same. Also same. So we can inspect any file that we like. Here we go. Well, this is interesting. It's loading low and high byte into AE in memory, which is way down in 0 page. And it's interesting because AE in memory is the pointer, the undirected pointer, where it actually loads bytes from the disk drive into memory. So it's loading data straight into the pointer, and then it's loading a new value into the low byte of the pointer, which changes where it actually loads. So it's trying to obfuscate slightly where this data is being loaded. And actually it's loading 088C, it's loading that at 3F, because after it loads the byte and stores it into memory, it does an increment of AE and AF. So AE, AF, AE in particular would contain 3E, and then it does an increment, so it would start storing the next byte at 3F. So let's validate that in the machine code monitor. I have some useful debug label files here, so a lot of the 0 page and the kernel entry points are actually documented now in this label file, and also it's got some breakpoints which for me are going to be useful for breaking into kernel serial I/O functions. So let's use the playback command to load those labels and those breakpoints. There we go. This is going to make it a lot easier to debug the code, because we'll see labels rather than trying to remember which kernel calls are which. So these are the current breakpoints in the kernel that are set up, mostly to do with serial I/O. We want to watch what happens when we store to AE and AF. This is the breakpoint to send listen command. I'm going to disable the breakpoints for the serial I/O at the moment, because I want to really run quickly through to where it sets AE and AF. If I expand this window over, you can see the much longer, much easier to read kernel symbols. F51C is what I want. Yes, there we go. That's the store of the bytes coming in from the disk. It's just executed 1 byte store already, we can see from this CPU history. So it's stored the byte, looking at this, the accumulator 3E in hex into the indirected address at AE and AF. And AEAF is 3E00. So we can see that the kernel disk loading code has successfully already rewritten the memory address to start storing the rest of the file data, which is going to be 3E incremented by 1 is going to be 3F the next time around. It's pretty standard stuff so far, apart from this loading address obfuscation, which I'm quite surprised by it, to be honest. Let's just set up the computer memory view with AE and AF so that we can see when we're debugging this an easier view of the indirected memory address that we're going through. So we'll just set that up here. There we go. Let's delete the AE AF update. Yeah, let's get rid of it. Don't need it right now. Let's just work on the byte stores from the disk load routine. So here we go. This is storing A, the accumulator, which is 08. And we can see here 08 comes from the file. So we're on track so far, and it's going to store it into 3F, way down low in 0 page. Now, we have 6 pages, so roughly 6 times 256 bytes of data to load from this file. So my initial thought here is that it's going to go all the way up through 0 page memory until it hits location AE again. So we can see it's loaded the beginning of the file data way down low into 0 page, because we saw that the 2112 sys command in BASIC, we saw that, and we saw the message. So I'm really intrigued now to see how AE and AF is going to get written as we store into it. This is going to get interesting. It's rewritten it once. I have a feeling it's going to rewrite it again. Let's keep on stepping. Nearly there. AA, AB, AC, AD, AE. And it's trying to load, and it's trying to store the value in the accumulator with 7.1 back into AE. So it's rewinding the memory store address back to 7.1 in hex. But it's still reading bytes sequentially from that file data. So it's rewriting what it has already loaded with new data. Well, that's rather intriguing, and it's putting it back again before AE, so it's rewriting it again. Okay, cool. Yeah, so there's the 7.1 in the file. We can see that we've got a sequence of zeros. We can see that it's not always going to be the same, because the kernel is going to be updating these registers. So this one is 1 out, you can see. Instead of 1995, it's 1994 in the file data. And of course, this is going to be, in memory, it's going to be 9F, A0, A1 and A2. In 0 page, A1 and A2. So no wonder the kernel, it's been updating it slightly, but we can see there are other 0 page locations that are untouched. So yeah, basically it's not loading this data perfectly sequentially from the file into memory. It's streaming bytes in, and then at the moment it seems to be partially sequentially and hopping backwards and forwards, or at least backwards, into storing into memory, and sometimes more than once. And of course it's storing B2 this time. So B2 is actually jumping ahead as opposed to jumping behind or previous. Interesting. So now it's loading a whole bunch of memory, and this whole bunch of memory is then going to, it's not going to, well, okay, so it's gone backwards again, actually, sorry. Yeah. And it's counting up again, so it's gone backwards, and now, so we're going to see where it rewrites it this time. Yeah, that B2 went into 7.2 memory, right? And this time it's going to write BA into AE, so actually BA is here. There we go. So it's hopping ahead now. It's avoiding AE and AF rewrites now, so that we now know that unless there's any other weird interactions with zero page, we're pretty sure that the bytes it's going to be reading from disk are going to be stored sequentially now into memory, probably until it hits some of the vectors up in extended zero page. So all of this data, there's a whole bunch of twos here. Probably where the stack is, but we'll have to verify that later on. And we can see that there's some messages coming along. So let's put quite a broad breakpoint in to see when the load code transitions into the code that we're actually loading, the kernel load into loaded code, because we know that we're going to get into these vectors at some particular point in time, so we want to trap out the vectors. I always forget. Okay, there we go. Right, now let's just let it load. We'll get rid of the breakpoint there for the store, for the bytes coming from disk, storing into memory, and there we go. So it starts running code, wow, right down low in ED. This is intriguing. It's ED has it's loaded code into 32A. Oh, sorry, it's loaded data into 32A, so it's got all the way up to the vectors. Okay, and it's got to ED. Well, there we go. The stop vector is at 328, 329. So it's just finished loading the stop vector, and it's jumped into code at ED. And this is code that has been loaded. And we can see it's doing a check for memory being loaded up until 33B. And then once it reaches 33B, it then runs this extra code, which does a load, EOR, and then store. And of course it's loading with a value which has also been loaded during this load cycle. F6FB handles errors, but it seems to be then using, okay, and then it runs through an indirected, okay, so an indirected jump. Let's see exactly what this code does. It goes to clear chun, which is clearing input-output channels, isn't it? Let's see what happens when we run the code through the kernel. We put those breakpoints back again. We'll see where it gets into our code. So yes, it's doing it's skipping those unlisten and untalks, and that's because 9. Okay, the configuration 0 pages cause that to just basically skip. And then what does it do? It's going to F12F, F12F. Well, I'm assuming it goes to F12F. F12F is, yeah, restore the IO device. Restore IO to default devices, yes. And it says that you're already at default devices, so don't do anything. Interesting. You see, it would have sent an unlisten, but it didn't need to because it noticed that the configuration was set up. Right? Because that's what was loaded during the load. So it fools the routine into thinking that the default device is already set, even though it's doing a load from disk. And then I don't think there's an error. So it just pulls and then RTSs. Okay. And then, because there's no problem, it uses the RTS to then go back into the kernel load, right? F501. which does a receive data, and then it does a store. Is that right? Yeah. Yeah. So it uses the process IO errors and skips everything and then just pulls whatever was there off the stack and then returns back into the load. That's a little bit of obfuscation there, isn't it? It's trying to hide the execution of getting back into the code in the stop vector, which is a code that's just been loaded, which does this memory byte loading check. So that hasn't hit again, so it goes back and round and around and around. So it's basically partially circumventing the load, but it's still running the load with this little nice obfuscated path through the stop vector again, and then through the kernel handle errors routine. Wow, that makes it harder to trace through, and that's obfuscation, so it makes it more difficult to understand what the code's doing. Eventually, once the memory address for AE and AF reaches the correct value, which in this case is 33B, it then sets the stop vector. So the stop vector isn't this code anymore. The stop vector is going to be pointing to ED, not ED on its own. So it stops running this code. It's going to run to ED. So it's loading some stuff up through the vectors. So with the updated stop vector now being unhidden, if you like, to 2ED in hex, we're going to set some kind of exclusion breakpoints, if you like. I don't want to have the breakpoint triggering for this little block of stop vector code as it's currently running, but I want to break on any other code execution anywhere else in memory. So we're going to do that. We're going to put the breakpoint there as well. And we can see that we get into code which is starting at 2ED now. The code at 2ED has hex bytes 4C and B2, and I expect that we'll be able to find that in the file. We can just verify here that it comes from the stop vector, which comes from just after executing the standard kernel load routine, which does that indirected store into AE and AF, the low and high byte, remember. We can see that it's starting to do this updated stop vector code now when it reaches about 33C that we can see in the memory view there for AE and AF. So this load here at 2CF is interesting. The first time round the load is there in memory for the load instruction, but then it gets updated at 2E1. We can see that it's getting updated with the store. At 2EA in hex there is a jump F6FB, which is also kind of suspicious. So there we can see in the file data on the disk that 4CB2 and so on and so forth is loaded into memory at that point. Gosh, so the file data really does move around in memory quite a lot when the kernel load is loading it around, because it was modifying AE and AF as it goes along. I'm just enabling here the breakpoints for the kernel I/O. I just really want to make sure that we're not missing anything as this code still continues to use the kernel, because the jump at F6FB is a little bit suspicious. I'm also adding the breakpoint at F51C, which, if you remember, is the kernel standard load routine which stores the byte from disk. There we are, it's just done, or it's just about to execute the store there, and we can see that the load indirect has been changed to a store indirect. So this code now looks like it's doing a stop vector trap which loads from memory what was just stored by the kernel loader perhaps, and then EORing it with some various values, and then storing it, basically de-scrambling what has just been loaded from the disk as it's loading, which is a really fantastic bit of obfuscation, if you like. The load has loaded some obfuscated memory into 0 page, claimed the vectors, updated the vectors, and then is using code which has just been loaded within the same load as it's still going on. It will then start to de-scramble the data, which is great. So where are we in the history here? Yeah, we're just coming out of the received data. You see, these labels make it a lot easier for understanding what the kernel code is doing, right? So we're going back into the kernel routine again for the rest of the standard kernel load routine for receiving data from the disk, and then it comes back through the stop vector, which goes to B2, which goes to here, and then we decrypt what was just loaded. Yeah, gosh, seriously, this is very obfuscated code execution pathways. So we can see here that the code at 2EA, which is the code which was just loaded as part of this data load from disk, is jumping into F6FB, which does this kernel IO message update, error message update, which doesn't display any error messages because there's no status byte saying that there's an error message. And then it goes back to 322, which then follows through with the vector. It follows through, checking a few things, doesn't do anything, pulls the status off the stack apparently, or pulls one byte off the stack and then returns, which then comes back to our code. Well, comes back to the load code, which then goes back through the stop vector check, which then comes back to the code which was just loaded, which does the de-scramble. So this is, if we have a look at the text in memory, it is Paraprotect version 2, 1987. So this was developed when I was around about 14 years old. These modern tools allow us to easily see, or more easily see anyway, the code execution pathways that this is doing. Imagine trying to debug this without a cycle accurate single step debugger with non-invasive breakpoints and memory watch points. It would have been very hard. It would have involved disassembling a lot of stuff which is in memory, trying to analyze by brain power. Now we've got to 203 because we set up those exclusion breakpoints again. We can see that it came to 203 because F657, if we... Yeah, F657 is the end of the kernel load, and then it's just doing an RTS, so it's basically pulling... I'll just double check that, F657... Yeah, there we go. It's the end of the standard load routine. So the standard load kernel load routine has completed because there's no more data from the disk, and it's doing an RTS. Now if we have a look at what the stack pointer is, it's just pulled the RTS. We can see the data that was loaded from the file. These 02s here are basically filling the top end of the stack. Now as the load is going on, it's okay, but then when the kernel load routine finishes, it reads these updated values from the stack. And this is a stack slide. Repeating byte values in the stack will then get pulled off, and no matter the alignment of the final RTS, you're guaranteed to get 0202, which with +1 for the return address for the RTS, we get to 0203. So this stack slide is always guaranteed to execute code at 0203. This is why we get to the code at 0203, is because the stack slide has told the kernel load to return from subroutine back to this address. we didn't call from this address, but the stack was updated to say that we had called from this address. That's why the kernel returns to this address. We can see here that we've got a whole bunch of memory filling by the looks of it, up until 21F in hex. Shifting right, Control V probably turns the screen off at this point. Not too interested in that, but it's probably what it's doing, and it's turning the screen black. It's allowing stores to memory everywhere. You can see, look, in the graphics maps, in the text screen, if we go all the way up through RAM in the text screen, we can see that it's been filled with this repeating pattern every 256 bytes, but it's, you know, not trivially compressible. I mean, yes, it's a 256 byte repeating pattern, so a more advanced, say, dictionary-based compression method would be able to compress it, but an RLE method would not be able to compress it. We're just in the interrupt service routine here. That's okay. IRQ service routine, and it's going to the standard IRQ service routine. We'll just exit out of this at this particular point in time. This just triggered because of the clear interrupt, because of the kernel in it, zero page vectors doing its thing. This is because it called here the kernel init IO. That's, you know, fine. So this newly loaded code, which is basically de-scrambled code from the disk file, is now executing some cleanup. It is confident that it has control over the computer, so it's doing a whole bunch of extra EORs and stores. We can see where it's starting to store it. It's 23B. So again, we'll put a breakpoint here. Because these are non-invasive breakpoints, we don't need to worry. And we can see now that it's decrypted or de-scrambled a load of code, or some more code, which does extra stuff. So this, what is this doing? Okay, it seems to be storing stuff into 8000 in hex, which is sometimes where cartridges appear. It is storing the result of that into extended zero page at 200. It is storing a whole bunch of data into that address. It's trying to clear that RAM again with those repeating values. Okay, it looks like it's trying to trigger something in the IO, the extended IO vectors, which are basically usually claimed by cartridges that are plugged in at DE and DF00. So it looks like this is some kind of like cartridge code. We can see actually that the last loaded address is AE and AF is 05EB. If we look up in the memory of the computer. And here we go into code at 3B2 now. So it's tried to do some cartridge defeating code by the looks of this. Ah, no, what it does is that it's taken the code at 200, stored it into the RAM. Now, if there's a cartridge plugged in, it won't be RAM, it will be ROM, so it will read back the wrong data from the ROM. If it's RAM, it will read it back and then store it back into 200. So, yes, it's detecting for ROM being at 8000. There shouldn't be ROM at 8000, of course, because the game is running. Well, the game protection code is running anyway. So then it runs into this code. This code does it does a raster check. Okay. It then sets up some timer values. Okay. It then runs what looks like a whole bunch of weird opcodes. So it ran the whole bunch of weird undefined opcodes, which do some stuff, but it doesn't actually do much. It seems to be there to waste some time, and it seems to be there to waste some time before it gets to some more real code here. So, okay, This code here is where it looks like it's finished the load from the disk. So it's going to 38C. 38C does, oh look, 38C loads the current. BA is usually the 0-page register which contains the last device that was loaded from. So in this case, BA, yep, should be 8. There we go. Current file device number in the memory view for the computer. We can see that. So what it's doing is that it's doing a whole bunch of standard kernel I/O calls again. So this time it is, well, it looks like it's sending data from 3AD and also 396. Looks like it is also doing a little subroutine to set the drive into listen mode and also set up some 0-page variables. It actually doesn't get to this breakpoint here at 3AA. There is a jump and it returns at 393. So we're not going to be worried about that. It just sends a listen and a secondary address using using the kernel I/O here. So it will return from this jump. So we'll just jump over these. Hopefully, here we go, boink, right, standard kernel code, right, and then it comes back to here. So yeah, this is standard kernel stuff. It's just sending information to the drive. Now, using the low-level serial routines in the kernel, it's basically sending bytes to the drive with commands. And if we have a look at, so if we have a look, yep, here we go. There's a backwards memory execute with a low and high byte for the address. So it looks like it's going to start executing code in the drive at 205. So it's doing a memory execute, which this is kind of like programming the drive with code and then executing that. I want to set a broad breakpoint range in the drive so that if there's any misunderstood code execution pathways here, then we'll find it. But basically, I'm pretty sure that 205 is going to be the code execution address for the code in the drive. But let's do a break. Let's run ahead. Let's remove the breakpoint here because I'm not interested about that. Okay, it's now sending the second chunk of data after the memory execute, I think, which does 396. Look in the right memory. There we go. 78A9. Well, that's set interrupt load accumulator. So yeah, we can pretty much safely say that it is trying to run stuff in drive memory. So it sent the memory execute, and then it's sending a whole bunch of extra bytes which gets stored into drive's memory. So 78A91285OE85, right? 85 I think is store accumulator 0-page, and then it sends an unlisten. It sends all of this data, and then it sends an unlisten to the drive, and then the Commodore 64 is at 365 eventually. There we go. Right. So what does the code on the Commodore 64 do? First, don't forget we've got the breakpoint in the drive as well for the execution, so that's okay. We're not going to miss that. But this code here just basically does. Oh, well, look at that! It does a great big long wait. And there we go. The code in the drive has hit this code. Now, you'll note that the bytes it was sending are then obviously received after the memory execute command. So it's basically sent these extra bytes hoping that the drive will store them in the buffer, which it has, and then it tells it to execute the code that was just sent to the buffer. Which is quite a clever way of doing it. It means that you don't have to actually do separate memory writes because the drive has done the memory writes for free. Isn't that fantastic? Lovely of the drive to be able to do that. And this code does a few different things. So while the Commodore 64 is doing this great big delay, we can see on the Commodore 64 that the delay loop hasn't finished counting down yet. It's only about halfway through, because it's counting with X and Y registers for 256 cycles, is it? Something like that. Anyway, yeah, that's a large number of cycles being wasted on the Commodore 64 side, but the delay is to give enough time for the drive to read the track and sector into a specific buffer. There's some self-modifying code after the track and sector has been, run, and then it modifies the code to then read a different track and sector in the drive before finally running to the modified jump address at 703. Okay, fine. So it loads 2 blocks into 2 different buffers for the drive code. And it loads those blocks directly from the disk itself. It doesn't execute that code from what was sent from the Commodore 64, which is a more efficient way of doing it, to be honest. I'm surprised at this point that the code wasn't scrambled. You know, I'm surprised that there wasn't a little de-scramble routine running on the drive to de-scramble this information just before it finally jumps to it. But then the code, you see at the moment the block, buffer 6 data space is empty. It's not buffer 6, that's buffer 4, but it's at 600 in hex. Now after it's finished the track and sector load, the Commodore 64 is still doing this delay loop. It's just about nearly going to finish the delay loop. It's got a few more iterations to go, but the drive itself has completed because it's going to run the code at 703. So we can verify now, I think, that the block at 600, the block at 600 now contains data, whereas just before, if you look up above, it was zeroed, completely empty, and there we go. The drive code now is doing pretty much standard stuff. If you remember my previous videos, then the drive address 1800 in hex is the VIA. So it's just basically waiting now. It looks like it's waiting for signals from Commodore 64 over the serial bus. There we go, the drive code is sitting there, waiting. We'll put a breakpoint just after the wait, just to really verify this. But the Commodore 64 is still doing this delay loop. We'll execute now, and then there we go. The Commodore 64 has finished the delay loop. The drive is still doing this wait for a signal from the Commodore 64. Seems to be setting up some values for the serial port on the Commodore 64 side and putting them into 0 page. And there we go. The Commodore 64 has done a serial port update, and then the drive code is no longer in that loop waiting for a command. The Commodore 64 now seems to be sending data to the drive. It looks like it is in 2 bits at a time, so it looks like the Commodore 64 and drive communication is a 2-bit protocol, perhaps, looking at this, with obviously a sync check for the drive code, because the drive needs to make sure that the Commodore 64 is at the same wait state as the drive is expecting before it sends back a whole bunch of optimized data in 2-bit transfer mode by the looks of this. So yeah, this is just basically a 2-bit turbo loader by the looks of it. And then there's some final stores into 9091 with a store here. So yeah, we can see that it's starting to store data into low and high of 90 and 91 in hex, which is 800 in hex, in directed. The code at 51F, after it does all of this loading from the drive and storing into Commodore 64's memory, 51F does a PLA, stores back into 1, restoring the restoring the state for the processor port, and then does an RTS. And I bet the RTS then runs some other code which has either been loaded or just been loaded. We'll get to there in a bit. So if we have a look at them, we're going to delete some of these other breakpoints. There we go. Yeah, we can see on the memory view now in ICU that it's doing a very fast load. The RTS is triggered, and there we go. So it's jumping to basic start. Basic start code starts with what looks like some undefined opcodes, but it very quickly gets into a set interrupt, claims all of the stack with a load X with FF and TXS, which transfers the X register to the stack pointer. So we have a whole bunch of code which was just loaded. If you look at the graphics bitmap views side by side for the first two banks, the data looks really quite well compressed. This is kind of like very expected kind of standard Packer decompression code. There's 1, 2, perhaps even 3 passes of decompression going on here. There you go, there's the initial memory move. Yeah, we can see it's moved the memory all the way up at the top. Standard stuff really, right? Move what's in lower memory all the way up to higher memory first, and then run a bunch of packing, decompression, depending. So in the early days, when dictionary-based compression algorithms weren't so mature, it was more efficient to do a run length encoding first and then to compress the result of the run length encoding. So this is often why you would see more than 2 or more decompression passes going on. Then later on, dictionary compression got so efficient that there was no real gain from doing RLE first, or there was no real gain in doing like a sparse packing compression method. So generally speaking, the whole of memory would just get compressed with a dictionary compression algorithm. You didn't need a depacker, a run length decoder, and then a dictionary decompression. You just needed the dictionary decompression. And that would save you the overall memory, because you don't need 2 or 3 copies of a decompression or depacker in memory. So look, it's put a whole bunch of code on the processor stack, and then it's jumping to 1000 in hex. Well, this is not really a surprise, is it now? There we go. This is the final decompression. You can see that it might have been doing like a final RLE depack, because the RLE would have been the first pass. Obviously it's the last pass when it comes to decompressing the memory. So it was either an RLE or a depack. Unpacking is where you have usually sparse data that you want as separate memory chunks. You want to put them into the right place in memory, and there's virtually no compression there, apart from you're not compressing the blank spaces in memory in between. But doing that means that your memory map is left in a pretty much an undefined state. So generally speaking, I prefer to compress the whole of memory, including all of the blank data, as zeroed out data. It means that I'm sure that the memory state is in a known state where all of the memory is explicitly cleared to 0, for example. But this was produced in the old days where the tools were different. There used to be this pipeline from packing separate memory chunks and moving them into the right place then doing an RLE on that, and then doing a dictionary-based compression method after the RLE. And to be honest, my old tools from back in the day used to do that as well. You could see that in Tusari, you could see that in all of my other projects from the old days. Now, doing a dictionary-based decompression on the whole memory, including bunches of blank memory, is sometimes a little bit slower unless your dictionary-based decompression is optimized. Especially the dictionary copy loop, for example. If you optimize that better, then it's not too much slower than just skipping over the blank memory by doing a depack first. So then, after pressing fire on the intro screen, we can see that it's doing another load of game data, this time for level 1. There's a little bit of loading and storing going on everywhere. So I think we'll leave it there because this video is getting quite long already. If you enjoyed this video, if you enjoy these kind of technical deep dives into old retro games for the Commodore 64, then there is a button on this video specifically for that purpose. And if you want to subscribe, then I hope you do as well. Thank you very much for watching, and I hope to catch you again next time. Have a great day wherever you are.